Hey everyone, I am here with 6.5, which is the energy of phase changes. So, this diagram we're looking at is sometimes called a heating curve, or if it is the opposite, a lot of times it might look like this, where it is the inverse graph. That might be called a cooling curve. And so, what we're looking at here is the temperature changes and the amount of energy it takes to go from a solid phase, the transition between freezing and melting, and then liquid phase, and then the transition between boiling and condensing, and then gas phase. This is specifically for water because I know that they list ice, but if this was any other compound, this would be my solid phase, this portion of the graph. Where we see the flat line is where the actual phase transition is happening. Then we have our liquid phase. Again, because this is water, they wrote water, but if this was any other substance, that would be liquid phase. And then we have another flat line. That's where our transition comes between the water and the gas, or transitioning between liquid and gas. And then the final section is we're completely in the gas phase and that gas is just heating up. Now, we've been talking, at least in the last section, about the Q equals MCAT equation. Unfortunately, the Q equals MCAT equation can't be used for phase changes because this flat line where we see the phase changes here and here, the temperature does not change. That's why it's a flat line, is because the temperature is remaining constant. So if there's no change in temperature, that means Q equals 0? That should not make sense because we know that it takes energy to melt things and it takes energy to boil things. So how can Q equal 0? Well, it does not equal 0. And one of the things we need to do when we do a phase change is to use a different equation. Here we have the phase change equation. For melting and freezing, that uses a constant called the heat of fusion, or delta H of fusion, listed here. N in this equation is referred to moles. And then for boiling and condensing, the constant that we want to use is called the heat of vaporization. We want, again, to point out that N is equal to moles. The other thing that you can do is you can switch out moles for mass in these equations. And it really just depends on whether you use moles or mass and what the units are here for your constant. If heat of vaporization or heat of fusion has grams in it, that means we're going to switch out for mass here. If it's measured in kilojoules per mole, then we need to be in moles in order to use that equation. Delta H equals N times the heat of fusion would be for any melting process or freezing process. Boiling and condensing, we use the same equation except we switch out for the heat of vaporization. Now, here's the fun part, is that when you are freezing and when you are condensing, those are actually exothermic processes, and that's what's showing down here, because we will be taking energy away from the system in order to make that happen. So any time we do a calculation involving condensation or freezing, that's going to be an exothermic process, which means Q and delta H are going to be negative because energy is leaving the system. The other direction, if we are freezing something, if we are melting something, and then we are vaporizing something, both of those require energy. And so those phase changes are going to be endothermic. So Q and delta H for those processes are going to equal positive values. Let's look at a few example problems where we're going to utilize both our heating curve and this concept of the heat of fusion / heat of vaporization. So here we have a heating curve for methane, CH4, and we have different parts of the graph. Part P is going to be my solid being warmed. Where Q happens is the actual melting process. R is going to be in the liquid phase, and that liquid is going to be gaining energy. And then S is going to be the actual boiling or vaporization. And then part T of the graph is going to be my gas just warming up. So let's look at our questions they're asking us about this graph. The first is, how much energy does it take to melt 1 mole of methane? Well, they give us that number here in the graph as the delta H of fusion. Melting uses the delta H of fusion, and it tells us that it is 0.94 kilojoules per mole. So if I only have 1 mole, then it is exactly 0.94, and it's kilojoules. Now, because this is for melting, that means energy is going to be going into the system. This is going to be a positive 0.94 kilojoules, and that means that this is an endothermic process because I'm putting energy into the system. I'm actually going to jump down to letter C because letter C asks us how much energy does it take to freeze 1 mole of methane. Well, we're going to use the same equation. The heat of fusion is 0.94 kilojoules per mole. And if I only have 1 mole, then it is going to be 0.94 kilojoules. The difference here is that when you freeze, you have to take energy away from the system. So I need it to lose 0.94 kilojoules. And that's why this is going to be an exothermic process. For B and D, it's kind of the same idea, except we are looking at the vaporization value. They want to know how much energy does it take to vaporize 1 mole of methane. So delta H of vaporization, it tells me is 8.2 kilojoules per mole. I only have 1 mole, so this is going to be 8.2 kilojoules. And this is to vaporize, which means that I need to change it from a solid or from a liquid to a gas. That's going to require energy, so energy needs to go into the system, which is why this is endothermic. And then for part D, they want us to do the same calculation, but for condensation. For condensation, we use the same value, delta H of vaporization. Just like we saw with the freezing / melting though, what that's going to do is it's going to change the sign. It's going to be 8.2 kilojoules, but if I want to condense things, I need to take energy away, and that is going to be exothermic. So when we have vaporization / condensation, those use the same values, just like melting and freezing use the same value. All right, on the next example, they give us some grams and they want us to convert the grams into moles and then apply my equation. So if I take 9 grams and the molar mass of methane is around 16 grams, and that's grams per 1 mole, that means I'm going to have 0.56 moles. If I want to know how much energy is going to be taken or needed in order to complete this process, I'm going to take my moles, 0.56, and I'm going to times it by because this is a freezing process, I'm going to multiply it times the 0.94 because that's kilojoules per 1 mole. Moles and moles cancel. And so I'm taking 0.56 times 0.94. My calculator gives me 0.53, and that's going to be in kilojoules. Now, because this is freezing, that means energy is being lost. So I am going to give it a negative sign. I need to lose 0.53 kilojoules. On the next one, it's a similar calculation, except we are going to be using the heat of vaporization because they want us to do a condensation. So 45 grams. I know the molar mass of methane is around 16. So 45 divided by 16, I get 2.8 moles. Then to calculate my delta H, I'm going to take my 2.8 moles and I'm going to multiply it by 8.2 kilojoules per 1 mole. Moles cancel, And so I'm going to multiply 2.8 by 8.2, and I get 22.96. So I'm just going to call that 23 kilojoules. And it's telling us that this is being released, but also we know that condensation means that energy has to be taken away. So I'm going to go ahead and give it a negative sign just for consistency. All right, last example, we have determine the amount of heat needed to melt 125 degrees or 125 grams of gold if it was originally at 298 K. So one thing I'm going to do really quickly is go ahead and put this Kelvin temperature into Celsius by subtracting 273. And the reason I'm doing that is because my melting point is in Celsius and my specific heat is in Celsius. So I'm making sure that everything is in Celsius before I get this started. I think having a little graph is going to help with this to understand what exactly we need to do. Our bit of gold is starting at 25 degrees, and the first thing we have to do is increase the temperature up to 1064. Now, for this part of the graph where our temperature is changing, we can use the Q equals MCAT for this part. Then I need to flatline to actually do the melting part. I'm assuming it wants it to melt completely. So when we do the melting part, that's going to be Q equals N times the delta H of fusion. Once I have each of these Q values, I can then add them together, and that would be my final answer. I'm going to do the Q equals MCAT first. So my mass was 125 grams. It gives me on the table the specific heat of gold is 0.128, and that's joules per gram Celsius. And then final minus initial, 1064 minus 25 degrees Celsius. And this is going to get me 1664 or 16,624. Keep in mind that when we do this equation, grams and grams cancel, delta or Celsius and Celsius cancel, which leaves me only joules. I'm going to go ahead though and put this into kilojoules by dividing by 1,000. And the reason I'm going to do that is because when I add my Q's, they both either need to be in joules or they both need to either be in kilojoules. So I'm going to go ahead and put this in kilojoules so that when I add them later, I'm saving myself a step. Next, I'm going to do the part for the melting, which is going to be moles times the heat of fusion. I need to first figure out how many moles this is by dividing the 125 grams by 197. That is the molar mass of gold. So if I divide 125 by 197, I get 0.63 moles. So I'm going to do 0.63 moles, and I'm going to multiply it by the heat of fusion, 12.55. And that's kilojoules per 1 mole. Moles and moles cancel. 0.63 times 12.55 gives me 7.96. So I'm just going to go ahead and call it 8.0. And that's in kilojoules. So now to get the final amount of energy it takes for this whole process, the part to raise the temperature up to the melting point and then to actually melt it, I'm going to add those two numbers together. So 8 plus 16.6, and I get 24.6, and that's going to be kilojoules. That's the total amount of energy needed to complete this process. All right, thanks for joining, and I'll see you guys next time.